All right, and back for the final part of our final lecture, looks like. We were doing molecular energy diagram or molecular orbital diagrams in the previous page here. And I just wanted to go on and look at a couple of more and point out a couple of things. Table 8.3 on page 433 or 443 in the textbook has a list of molecular electron configurations for the first several elements, along with their bond orders and whether they're stable or not. So you can, if you want to practice doing those, you can always look there to, to check your answers. And then let's see, the other thing I wanted to point out is that unfortunately, when you get into p orbitals in the valence shell, you can get the molecular orbitals moving around relative to one another. If there are 1 to 3 electrons in the p orbitals of the valence shell of the atoms that are making it into the bond, then the sigma p orbital is actually not the lowest energy orbital. The pi orbital in that case would be the lowest energy orbital. So if you have more than 3 p electrons in the valence shell of the atoms that are going into the molecular orbital, then the sigma p orbital is lower energy than pi p. And that gets a little confusing. I don't actually expect you to remember that. If I were to give you a question where you have to do an orbital diagram like one of these, I would draw in the orbitals themselves. And I may not label them, but I would at least draw them in so you know where they are. And then you would have to fill in the electrons, that kind of thing. So you wouldn't have to remember whether the sigma p or the pi p orbitals are lower or higher in this particular case. So I'll take care of that for you. If you're doing a molecular orbital diagram for ions, then it should be based on the molecular orbital diagram for the molecule. That is, the combination of the two atoms without a charge. And removal or addition of atoms or of electrons basically just goes according to what we've always been doing so far. So if you have to remove an electron, I'm sorry, that got a little crowded there, but if you have to remove an electron to form the ion, that is if it's a cation or positive ion, then you remove the electron from the highest energy orbital present. So in this top example here, that would be this one right here, the sigma star 2p antibonding orbital. That's where the first electron out would come from, if there were an electron there. Of the electrons that are actually there, and if you had to remove one, then it would be one of these electrons here in the pi 2p bonding orbital, molecular orbitals, that would have to go. If you have to add an electron, in order, in other words, if it's an anion or a negative ion, then you just add the extra electron into the lowest energy position available. So if I had to add an electron to this example here, the first electron I add would go into the sigma 2p bonding orbital. So it would go there. Okay. So looking at C2 or carbon, diatomic carbon. Each carbon has an electron configuration of 1s2, 2s2, 2p2. We're only concerned here with the valence shell. So if we look at the s atomic orbitals, each s atomic orbital for the valence shell has 2 electrons in it. So you've got 2s2 for the carbon on the left and 2s2 for the carbon on the right. When they come together, they form sigma 2s bonding a molecular orbital and a sigma star 2s anti-bonding orbital. And you've got 4 electrons, so that's enough to fill the bonding orbital and the anti-bonding orbital. So they're all filled. For the p electrons, you've got 2 electrons in the p orbitals of the second shell for each carbon. So for the 2 p orbitals for the carbon on the left, that's 1 electron in each of 2 out of the 3 p orbitals, and the same on the right. When they come together to form molecular orbitals, this is a case where the pi 2p orbitals are lower in energy than the sigma 2p orbitals. And that's why there are two spaces down here on the bottom and only one here. And so you've got 4 electrons. So the first one would go into one of the pi 2p molecular orbitals. The second electron would go into the other pi 2p molecular orbital. And then the third and fourth electrons would just create pairs in each of those orbitals. And so that would be your molecular orbital configuration for C2. The bond order would be 1/2 the number of bonding electrons, which is 1, 2, 3, 4. Wait a minute. In the valence shell, that's actually going to be 6, isn't it? 1, 2, 3, 4, 5, 6 bonding electrons minus 2 non-bonding electrons. That 6 minus 2 is 4. Sorry. And so that means a double bond for C2. Okay, almost missed out on that one. The electron or the electron configuration for the molecular orbitals would be sigma 1s2, sigma star 1s2, if you want to include the core electrons. The valence shell would be sigma 2s2, sigma star 2s2, pi, wait a minute. Okay, sorry, I had the orbitals the other way around mistakenly originally, and I redrew the diagram, but I didn't redo the electron configuration. So for the valence shell, it would be sigma 2s star. Oh, yes, sigma star 2s2 and sigma 2p, or sorry, pi 2p 4. 1, 2, 3, 4. The others I crossed out were just because I wrote down all of these orbitals and I just crossed out the ones that turned out not to have any electrons in them. Okay. All right, so nitrogen, each nitrogen would have an electron configuration of 1s2, 2s2, 2p3. And so on the left-hand side, again, we're going to forget about the core electrons. So looking at shell number 2, that's the valence shell. The 2s electrons, you're going to have 2 s electrons in the valence shell for each nitrogen. So 2s2 on the left and 2s2 on the right. And when they come together to form molecular orbitals, the bonding molecular orbital and the anti-bonding molecular orbital would both be filled for the sigma 2s orbital, molecular orbitals. For the p molecular orbitals, or the molecular orbitals based on p electrons anyway, we have 3 p electrons in the second shell for each nitrogen. And so they will fill their atomic orbitals individually for both nitrogens, the one on the left and the one on the right. The pi 2p molecular orbitals are lower in energy here than the sigma 2p orbital would be. And so you've got 6 electrons total to deal with. The first one goes in the pi 2p molecular orbital on the left. The second one would go in the other pi 2p molecular orbital. And then the third one doubles up and the fourth one doubles up. And then 5 and 6 both go into the sigma 2p molecular orbital, because that's the next lowest energy position available. The bond order in this case would be 1/2 of 8. You've got 8 bonding electrons here. 1, 2, 3, 4, 5, 6, 7, 8, minus 2 anti-bonding electrons. So that's 1/2 of 8 minus 2. 8 minus 2 is 6. 1/2 of that is 3. So N2 forms, and it has a triple bond, which is not surprising because we've been drawing N2 quite a bit when doing Lewis structures, and it does indeed have a triple bond. The molecular electron configuration would be sigma 1s2, sigma star 1s, sorry, 1s2, sigma 2s2, sigma star 2s2. Wait a minute. Yeah, sigma star 2s2, that's this. Sigma 2p2, that's this. And pi 2p4, and that would be these two here. I ordered them the opposite way around in the electron configuration, but the actual order in which you write the orbitals in electron configurations doesn't really matter, as long as each orbital has the right number of electrons in it. Then we can go on to oxygen. Oxygen has, notice also, no unpaired electrons in N2. And that explains why N2 is diamagnetic. In other words, unaffected by magnetic fields, because all of the electrons are paired up. Oxygen, on the other hand, is paramagnetic, and we're about to find out why. Each oxygen has an electron configuration of 1s2, 2s2, 2p4. So for the 2s atomic orbitals, each of them has 2 electrons in them. And when they come together to form molecular orbitals, they basically fill the sigma 1s bonding orbital and the sigma star 1s antibonding orbital. For the p orbitals, for oxygen, the sigma 2p molecular orbital is the lowest energy molecular orbital here. So that's one continuous line there. Notice there's a gap between the two horizontal lines here, and that's because that's the pi 2p molecular orbital. Each set of p orbitals on each oxygen has 4 electrons. So a pair in one of the p orbitals and single electrons in the other 2 for each of the 2 oxygens. That's 1, 2, 3, 4, 5, 6, 7, 8 electrons to deal with all together. So you start filling them in from the lowest energy on up. First one goes here, second one goes here to pair up the electrons in the sigma 2p molecular orbital. And then the third one would go into one of the pi 2p orbitals. And the next one would go into the other pi 2p bonding orbital. And then the next one after that pairs up with one of the electrons in the pi 2p bonding orbital. And the next one after that pairs up with the other electron in the pi 2p bonding orbital. And you still got 2 more electrons to go. That's only 6 electrons that we've used so far. We've got 8 in the p orbitals of oxygen in the valence shell. So there are 2 more. The next lowest energy level would be the pi star 2p anti-bonding orbital. There are 2 of those, and we've got 2 electrons left, so they fill singly each of those pi star 2p anti-bonding molecular orbitals would have 1 electron in it each. 2 unpaired electrons. That's why oxygen is paramagnetic. It's affected by by magnetic fields rather, because it has unpaired electrons. And this is the way that we can tell that it has unpaired electrons. Everything we've seen so far would lead us to believe that all of the electrons in oxygen are paired up, but actually they're not. And you can tell by looking at that. The bond order for O2 would be 1/2 number of bonding electrons, which is 1, 2, 3, 4, 5, 6, 7, 8, minus anti-bonding electrons, which is 1, 2, 3, 4. So 1/2 of 8 minus 4 is 1/2 of 4, which is 2. In other words, O2 forms and it has a double bond. Just like that. The molecular electron configuration, if you want to include the core electrons, would be sigma 1s2, sigma star 1s2. And the valence shell is sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p4, and pi star 2p2. All right, and that's the whole thing. The reason that the sigma 2p and pi 2p orbitals can switch places sometimes is due to what's known as sp mixing. It's a combination of the wave function for sigma s and sigma p that leads to lower energy for sigma s, but higher energy for sigma p orbitals. And the same happens for the antibonding orbitals. And this occurs when the s and p orbitals have energies that are similar. So for things like lithium, beryllium, boron, carbon, and nitrogen, but not for things like oxygen and fluorine and stuff like that. But again, I wouldn't expect you to know which are which. I would draw the actual molecular orbitals for you and have you fill in the electrons. And also you might have to fill in the names of the molecular orbitals, but that shouldn't be too difficult. If there's, remember, if there's only one line for the molecular orbitals, on each level, then those are sigma molecular orbitals. The one on the bottom is sigma, the one on the top is sigma star, and then the subscript is whatever atomic orbitals they're formed from. So sigma 2s for this one, sigma star 2s for that one. And so this would be sigma 2p for this one here. But if there are two lines with a space between them on the same level, then that means those are pi molecular orbitals. And again, the subscript would be whatever atomic orbitals they're formed from. So these two orbitals here would be pi 2p molecular orbitals. These up here, since they're above the energy level of the atomic orbitals, would be pi star 2p orbitals. And the ones at the very top, since there's a single line there, that would be the sigma star 2p antibonding orbitals. Okay. And that brings us to the end of the chapter. This chapter went quite quickly, and I actually had to kind of pad out the number of homework problems with some even numbered problems. But I also did that not just because I wanted to make you do more work, but also because some of the even numbered problems were better than some of the odd numbered problems, frankly. So I gave you some better questions that way. I will announce due date for the homework soon. It's not going to be due really soon because we only just started the chapter, so I'll give you some time to do that. Like I said, we don't. Let's see. We only have for classes. Villa still has the rest of this week and then Monday, but that doesn't really give us a chance to do anything of significance in any other chapters. So I'm going to call this basically the end of the semester as far as our lecture materials are concerned. If anybody needs any help with anything, whether it's lecture or lab, get in touch with me. Just send me an email. My schedule is pretty flexible, so I can meet. I can respond to emails pretty quickly usually, and we can meet via Zoom if you want to, if it's anything more complicated, and we'll go from there. And then I'll announce. Actually, we're working on a quiz now. I'm hoping to squeeze in one more quiz before the final exam. The final exam is not really a final exam. It's just the 3rd hour exam, and it will cover chapters 6, 7, and 8. Okay, so it won't go back to the beginning of the semester, not explicitly. I mean, of course, there are some skills that that you use throughout the entire course that you'll need to remember from early in the semester, but I won't ask you explicitly anything from the earlier chapters. So 6, 7, and 8 is what will be on the 3rd hour exam. And that will be the 3rd hour exam. I will give out basically at the beginning of the finals period, and it'll be due at the end of the finals period. And I think the finals are from the 12th to the 14th. So I'll probably post it on the 11th and have it due by the 14th. And then grades are due soon after that. And well, I guess that's it. So, well, good luck and farewell. And maybe I'll see you in the fall around Villa when I'm probably going to be teaching physics again. So maybe you'll be in the physics class. Who knows? Just fair warning there. Okay, so until later, goodbye.